You know that feeling, right? Sun on your skin, maybe pulling a blanket close when it's cold. We all get heat and cold. But today on the Dope Dive, we're going a bit deeper than just the feeling. We're going to unpack, the real basics of heat, energy, and then stumble onto something truly, well, mind bending about water, plain old water. We've pulled together some great material that really gets into the science and, maybe surprisingly, the big real world effects. Our mission here is just to pull out those key ideas and make them, well, not just understandable, but hopefully pretty fascinating for you. Okay, so let's start with two words people often kind of swap around: heat and temperature.
Yeah, they sound similar, but they're really quite distinct concepts.
Right, so think of heat as like energy that's moving. It's energy in transit. We measure it in joules
Right.
usually.
Joules. Or sometimes calories, you might see that too. There's a direct conversion, about 4.186 joules per calorie.
Okay, and temperature, that's different. It's more about how hot or cold something feels, or, well, is a measure of its internal energy state, kind of.
Exactly.
Yeah.
It tells you the degree of hotness or coldness.
Okay, so with that baseline, heat is moving energy, temperature is how hot. Let's dive into this water thing. It's pretty unexpected.
It really is.
Most stuff, behaves predictably. Heat it up, it gets bigger. Cool it down, it shrinks. A metal bridge on a hot day versus a cold one, pretty simple.
That's the general rule, absolutely.
Ah.
Thermal expansion and contraction.
But water, between 0 degrees Celsius and 4 degrees Celsius, it does the opposite.
Yeah, it flips the script. In that specific little window, if you heat water, it actually contracts, gets smaller, and if you cool it, it expands.
That's the anomalous expansion we're talking about. And it sounds small, that range, but the effects are huge.
Absolutely huge. It really messes with our intuition, doesn't it? We expect warmer things to take up more space because, molecules moving faster, bouncing around more.
Right.
And that holds true for water outside that 0 to 4 degree range, but inside it now, something else is going on.
So if you take water right at freezing, 0 degrees C, and you warm it up just a bit, it actually shrinks. Its volume goes down.
Precisely. It keeps shrinking until it hits exactly 4 degrees Celsius. That's its point of minimum volume.
And the material we looked at mentioned that for 1 gram of water, that minimum volume is exactly 1 cubic centimeter right at 4 degrees.
That's the standard value, yes.
Yeah.
And then if you keep heating it past 4 degrees, then it starts behaving normally again and expands.
Okay. And the reverse works too, cooling water down.
Yep. Cool it from, say, 10 degrees down towards 4 degrees,
Yeah.
and it contracts, just like you'd expect. But keep cooling it below 4 degrees towards freezing, and it starts expanding again.
So counterintuitive.
It is.
And volume, the space it takes up, is directly linked to density, right? How much stuff is packed in.
Inversely linked, yeah. Density is mass divided by volume. So if the volume goes down, the density goes up, assuming the mass stays the same.
Ah, right, inversely. So as water warms from 0 to 4 degrees C, its volume shrinks, meaning its density must increase.
Exactly. It gets denser and denser, reaching its absolute maximum density right at 4 degrees Celsius. That's the point where water is heaviest for its volume. About 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter.
And then above 4 degrees, as it starts expanding again?
Its density starts to decrease again, like most other liquids when heated.
Wow. So what's happening with the molecules in that weird 0 to 4 range? Why do they pack closer when it gets a bit warmer?
Well, it's related to the hydrogen bonds between water molecules. In ice, they form a very open crystal structure. As it melts and warms slightly towards 4 degrees, some of that structure collapses, allowing the molecules to actually fit closer together, even though they're moving a bit faster. It takes that bit of energy input to break some bonds and let them snuggle in tighter, increasing the density.
Okay, that makes some sense. It's like the structure is collapsing inward a bit.
Sort of, yeah. Until about 4 degrees, then the normal thermal expansion effect, molecules moving faster and needing more space, starts to dominate.
Fascinating stuff at the molecular level. But is there a way to actually see this density effect in action? Not just imagine molecules. The sources mentioned Hope's experiment.
Ah, yes. Hope's experiment is a really elegant demonstration. It makes this density change visible.
How does it work?
Okay, picture a tall metal cylinder filled with water. And it has 2 thermometers, one stuck in near the top, let's call it T1, and one near the bottom, T2.
Got it. Top and bottom readings.
Right, and around the middle of the cylinder, you wrap a container with a freezing mixture like crushed ice and salt to cool that central section really effectively.
Okay, cool in the middle.
So you start with the whole thing at room temperature. Both T1 and T2 show the same reading.
Makes sense.
Now, As that central band of water starts to cool down from room temperature towards 4 degrees C, what happens? It gets denser.
Right, denser water. Sinks.
Exactly. So this cooler, denser water sinks to the bottom. And you see the bottom thermometer, T2, start to drop quite quickly. The top one, P1, doesn't change much yet.
Okay, so the bottom cools first.
Yes, and T2 will continue to drop until it reaches.
4 degrees C, the point of maximum density.
Precisely. It hits 4 degrees and then kind of stabilizes there for a bit because that's the densest water accumulating at the bottom.
Okay, but the freezing mixture is still cooling the middle, right? So that water goes below 4 degrees C.
And here's the clever part. As the water in the middle cools further, say from 4 down to 3, then 2, then 1 degree, what happens to its density?
Below 4 degrees, it starts expanding again, so it gets less dense.
Bingo. So this colder, but now less dense, water doesn't sink anymore. It actually rises. It goes up, floats up towards the top, and now the top thermometer, T1, starts to drop rapidly, going down towards 0 degrees C. Eventually, ice might even start to form right at the very top surface.
Well, the bottom one.
T2 stays steady at a comparatively warmer 4 degrees C.
Okay, wow. So the coldest water, the stuff closest to freezing, ends up at the top because it passed that 4-degree maximum density point and became lighter. That's a really clear demonstration.
It really is. It shows the effect beautifully.
So, okay, cool experiment. But you said earlier this anomaly has massive real-world consequences. This isn't just like a lab trick.
Oh, absolutely not. It's fundamental for life on Earth, especially in places with cold winters.
Yeah.
Think about a lake or a pond when the air gets cold.
Okay.
The surface water cools down. As it cools from, say, 10 degrees down towards 4 degrees, it gets denser.
And sinks.
Right, causing the water to circulate, mixing it up. This continues until the entire body of water, or at least a good chunk of it, reaches 4 degrees C.
Uniformly 4 degrees. Then what?
Then, as the surface continues to lose heat to the cold air and cools below 4 degrees C, say to 3, 2, 1, that surface water becomes less dense than the 4-degree water below it.
So it doesn't sink anymore.
It stays right there on top. This layer of colder, lighter water forms at the surface, and eventually, if it gets cold enough, that surface layer freezes solid.
Ice on top.
Ice on top. And ice, crucially, is a pretty good insulator.
Ah, right. Like a blanket on the lake.
Exactly. It dramatically slows down heat loss from the water underneath. So beneath that icy lid, the bulk of the water remains liquid, and importantly, the densest water at the very bottom is at 4 degrees C.
Which is cold, but not freezing.
Right. It allows fish, plants, all sorts of aquatic life to survive the winter down there in that relatively warmer 4-degree water, even when the air temperature is far below 0.
So if water behaved normally and just got denser and denser as it cooled,
Lakes would freeze from the bottom up. The coldest, densest water, ice or near freezing water, would sink, and eventually the whole thing could freeze solid. That would be catastrophic for most aquatic ecosystems as we know them.
that's incredible. A tiny quirk in how water molecules arrange themselves literally protects entire ecosystems.
It's a profound consequence, yeah.
But there's a downside too, right? The sources mentioned burst pipes. That sounds less helpful.
Yes, definitely less helpful for homeowners and infrastructure. It's the exact same principle, that expansion as water cools from 4 degrees C down to 0 and then freezes solid. Water expands by about 9% when it turns into ice. If that water is trapped inside a rigid pipe, that expansion creates immense pressure.
More pressure than the pipe can handle.
Often, yes. Especially with metal or even some plastic pipes, the pressure builds and builds as the ice forms and expands and eventually crack. The pipe bursts. You might not even notice until things thaw out and water starts spraying everywhere.
Nightmare scenario. And it affects plants too.
It can, yeah. The same thing happens within the tiny capillaries or cells inside plants. If the water inside freezes and expands, it can rupture the cell walls, causing frost damage, killing leaves, or even whole plants. That's a big concern for agriculture and cold snaps.
Is that why farmers sometimes flood fields if a hard freeze is coming?
That's part of the idea, yes. A larger volume of water has more thermal mass. It takes much longer to cool down and freeze completely. Plus, as water freezes, it actually releases a small amount of heat, called the latent heat of fusion, which can offer a tiny bit of protection to the soil and roots right near the surface. It seems counterintuitive to add water when it's freezing, but it can help buffer the temperature change.
Okay, fascinating. The same expansion saves the fish but bursts the pipes.
A real double-edged sword, that anomalous expansion.
All right, let's try and wrap this up. We started with the basics, just getting clear on heat being energy moving, measured in joules, versus temperature being, well, how hot or cold something is.
The fundamentals.
Then we jumped into water's really weird trick. Between 0 and 4 degrees Celsius, it contracts when heated and expands when cooled. Opposite of most things.
Reaching that peak density minimum volume right at 4 degrees C.
We saw how Hope's experiment makes that visible, the coldest water ending up on top because it becomes less dense below 4 degrees.
A great visual. Yeah.
And then the consequences.
Huge consequences. On the one hand, absolutely vital for keeping lakes and rivers from freezing solid, protecting aquatic life through winter, thanks to that insulating layer of ice forming on top.
Life-saving anomaly.
But on the other hand, that same expansion when water freezes causes major practical problems, bursting water pipes, damaging crops through frost.
Yeah. So here's something to chew on as we finish. Just imagine for a second. What if water didn't do that? What if it just kept getting denser and denser all the way down to freezing like most liquids?
Lakes freezing solid from the bottom up.
How profoundly different would our planet look? Would the ecosystems we know even exist in colder regions?
It's hard to even picture it. The knock-on effects would be enormous.
It really makes you think. This one, seemingly tiny detail about water has these massive world-shaping implications. Maybe it encourages you, listening, to look at other everyday things around you and wonder, what other normal stuff has some surprising science hiding just beneath the surface?
Yeah, what other common phenomena rely on these kinds of perhaps unexpected physical principles? Worth pondering.